Okay, seems to be recording. Great. So we're all set. Right. Thank you all for coming. So today we have Kiryl Pakrouski with us, who is at ETH. And so he's done a lot of work on various models from both condensed matter and sort of inspired by high energy physics and looking for weak electricity breaking. And he'll tell us about some of this stuff. So Kiryl, please go ahead.
Thank you so much for this possibility to talk about our results. So I'll be talking about weak electricity breaking today in the models that most of the condensed matter people are very familiar with. And this work has been done with Igor Klebanov and two of his PhD students and his current postdoc. All right. So the introduction will not be very long because I think this audience is more or less familiar with ETH and many body scars, in part because of a lot of work on that was done by Zlatko. But let me briefly say that the ETH, the eigenstate thermalization hypothesis, basically tells us that the expectation value of some meaningful observable M measured in every eigenstate should be following some kind of smooth curve given by the thermal average of the same observable in the same system. And this basically tells us that these outlier states, like these red states in the plot, they shouldn't be happening, that lay clearly far away from the thermal average. And there are some known violations of this. In particular, there is many body localization, there are integrable systems, and the topic of today will be the many body scars. So what do we know about them? So first, as I said, they violate ETH. Then you often find them somewhere in the middle of the spectrum. So here we have energy on the x-axis, and they are somewhere in the middle of the spectrum, which means they correspond to high temperature. They also often happen to have low entanglement entropy. And this does not need to be always so, but most of them have low entanglement. And in this way, in this perspective, they are similar to the ground states. And an interesting property, which has also been confirmed experimentally, is that if you initialize your system into a state which is a mix of the many body scars, then the system actually comes back to that state repeatedly over and over again during the time evolution, which has been termed revivals, and which is pretty interesting. And then there is this off-diagonal long-range order, which is not always the property of scars, but at least in our framework, all the scars have some kind of off-diagonal long-range order, and I will expand on this more during the talk. So why is this interesting? First, it's fundamentally new physics. We violate ETH, which is a cornerstone of connecting quantum physics to statistical physics. Then some people think about the quantum information applications, and the reason is that, well, I said about this revival, so when you initialize the system to some particular state, you could think of this as, you know, putting in some quantum information into the system, and then the system doesn't lose this information, even though the states are at high temperature. So could this amount to high temperature quantum memory? Is pretty interesting and exciting question, I think. And then the other motivation is that these states, the many body scars, they actually happen in many models that I used to describe unconventional superconductivity. And in addition, one finds this superconducting off-diagonal long-range order in these states. So this is additional motivation thinking about if possibly this phenomena could somehow be connected. And on the personal side, I've always been interested in quantum information and quantum computation, and then even had the chance of really doing this in experiment at very low temperatures. And so if there is a slightest possibility of doing this at room temperatures, I also find this pretty exciting. So now today,
sorry, what were you actually doing there?
That was the dilution fridge, and there were some superconducting qubits in there, and I was doing some computations, some 2-3 qubit gates on that, but from time to time you also have to refill this liquid nitrogen to keep them cold. And of course, if you wouldn't have to do that, that would be pretty interesting, I would say. Yeah, so that was, I think that was my semester project, something like this, when I was in the master study. All right, so today what we're going to do, I'm going to tell you about the general recipe we have for designing Hamiltonians with many-body scars, and then we'll consider in depth one special case of spin 1/2 fermions on a lattice. So there we will discuss the actual wave functions of the scar states, the long-range order, the Hamiltonian terms you can use to build those systems, and we will find that actually a lot of models that you see every day have the many-body scars. And then one new example we just wrote up recently is a similar case, but you have a multi-band system. So you have multiple flavors of fermions sitting on the same site, and we will see the implications of that as well. So the general recipe goes as follows. We will think of this whole circle as the full Hilbert space, and then we'll try to separate it into 2 subspaces. And moreover, we'll try to arrange for 2 different Hamiltonians to act in these 2 different subspaces. And then the hope is that if these 2 Hamiltonians are different enough, then these states will also have different properties and will not thermalize, will violate ETH. And the other observation that will be useful for us is the following. If we have a state which has some symmetry, so it's symmetric under some group, and for this example, let's just consider 3D rotations as a 3 group. So the observation is that all the generators of that group, which are just the projections of the total angular momentum, they do annihilate the states invariant under the group, which, well, you can see here. And then so this is true for this particular case, but this is also true for some bigger, more complicated groups that will appear later in this work. And now putting this these 2 ideas together, basically the proposal is as follows. Let's think of the green subspace as the subspace of the invariant states under some group G. So first we need to identify some group G, then we classify all the states in the Hilbert space according to the representations of this group. And then the ones that are invariant, let's put them into the green subspace. And then let's also take the Hamiltonian of this form, where H0 is something simple, and I will make it more precise what I mean by simple, but it could also be 0 or constant. And then OT is something which is proportional, where T is the generator of the group. And we just agreed that the generators of the group annihilate the invariant states. So essentially here in the green subspace, we will have the simple H0 Hamiltonian. Whereas all the other states, they will fill the full Hamiltonian, which can be made pretty chaotic and strongly interacting by the choice of this O. So the O is actually, there is almost no restriction on it, except that if you want the Hamiltonian to be Hermitian, then this OT needs to be Hermitian. All right. So the first question you may have is how to choose the group G. And this is actually, well, there is no prescription for this. I think it gives you a lot of freedom, creative freedom, the choice of this group. But 2 observations, one observation is that if you choose smaller group, then you will have more invariant states. So if you want to have, like, for instance, exponentially many scars, then you would like to choose a small group. And the other observation is that you may want to look at some Hamiltonians that you see every day and consider the terms that are there, and maybe find that some of them actually already are generators of some group. And that would naturally suggest using that group as the group G. And this actually will happen in both our cases. Now, the simple part of the Hamiltonian H0 What we really want from this is that it just doesn't mix the green states with all other states. Or you could say that these green states are eigenstates of H0, and that means that basically H0 will totally determine the energy. But you can also have this more general expression for the H0, which basically says that if you compute the quadratic Casimir of your group G that you choose with H0, then they need to commute on the green subspace, or they need to be proportional to this quadratic Casimir. So again, this W here that can be chosen to be anything because of the quadratic Casimir on the green subspace, this will be 0. And then a special case is when you have 0 on the right-hand side, and that just means that H0 respects the symmetry G that we started from. And that was the condition in general, just to have this dynamical decoupling of the invariant subspace. But you need to have more restrictions on H0 if you want to see revivals. And basically, you could say that the most general condition, it seems, to have the revivals is that there is a common divisor between all the gaps between all the green states, between all the invariant states. And then if that is true, then going through this simple algebra here, you see that actually you will have constructive interference between all the states in the green subspace. And then a special case of this is when you have a tower of equidistant states. And actually, interestingly, in a lot of examples in the literature, this is what you see. And moreover, in most cases, it's some kind of B-field Zeeman splitting that generates this equidistant tower. But this is a special case. So now I wanted to flash this slide as well. And this is, I say from the beginning, it's very far from my expertise, but I just wanted to highlight something. I wanted to highlight that in our approach, we think more about the Hilbert space. And these singlets, they are property of the Hilbert space. And then any Hamiltonian, the Hamiltonian becomes secondary, because any Hamiltonian of the desired form will have the phenomenon. And then I just found that it's pretty exciting. This particular paper applied the same idea to some other Hilbert space. In particular, they were thinking about ADS CFT correspondence. And then on the gravity side, they have a black hole, and they have this very, very stable orbits around black hole that they think might be actually the invariant scars. But we today will consider something much more down to earth. We'll consider the fermions sitting on a lattice. So spin 1/2 fermions. So on each side, you can have either nothing, you can have up, down spin, or you can have both fermions. And they are created or annihilated by the standard complex fermionic operators. Now the lattice that we'll consider, actually, for us, it will not matter the dimension of the lattice. So it can be 1-dimensional, 2-dimensional, 3-dimensional, any other dimension. N will be the number of sides in the lattice. And here it's labeled this particular 2D lattice, for instance, it's a bipartite lattice. And for some of the scar families, it will be important that the lattice is bipartite. For some others, it will not be important. So now that we agreed that we have these 2n flavors of fermions, then, well, because there is one fermion, up to 2 fermions sitting on each side, so then U2n is the biggest group acting on this Hilbert space in principle. And so if we wanted to ask the questions what G I can choose, then this would naturally be some subgroup of this huge U2n. And now another interesting observation is that if you just take hopping on a lattice like this, then you can actually show that it closes into an SON or SUN algebra depending on the amplitude of the hopping. So that naturally suggests that we can actually use one of these groups as the group G in the general prescription. And we will actually, well, it's a little bit longer story, but you will actually find that the invariant states will actually have a little bit bigger symmetry. So we require only this SON or SUN, but the full symmetry will be a little bit bigger. So then what you can do, you can actually build the invariant representations of those SON or SUN in this Hilbert space. And I'll be talking about the two families of states, although there are three in total. So I have here on the left Zeta states, and then I have Eta states on the right. And what I'm not showing you, there is also, so these states are actually Eta prime states, we call them. But there is also Eta states which don't have this exponent here, but a lot of their properties are the same as this family. So I will only discuss two families. So so basically, they all work like this. You have some state from which you start, and then you have some operator, which basically switches. So there are n+1 states in each family, and they all differ by how many times you applied this raising operator to the state you were starting from. And I will expand a little bit on the physics of the states in a second, but I also wanted to mention that this Eta prime states, they were already found to be eigenstates of Hilbert model by Young, by the famous Young in 1989. And so this is his paper. So he wrote down the raising operator, he wrote down the wave function, and he actually even discussed the long range order that they have. But it's actually pretty exciting, I think, that he found it from his considerations. We arrived at the same exact expression by just writing down the SON invariant representation in our Hilbert space. So it's pretty exciting. We get the same expression. So now let's discuss what is the physics of the state. So the zeros at a state is just nothing, the vacuum. There are no particles. So then the first Eta state is when you take what you could call a Cooper pair. So you have two spins sitting on the same side, and you make an equal superposition of putting this pair anywhere on your lattice. And here I show the 1D lattice, but again, it could be any D lattice for all purposes. And then the second state is when you take two pairs and you put them again in all possible places, and you continue this until you filled the whole lattice. And so adding this pair is basically done by this stepping up operator. So those were the Eta parent states. Now the Zeta states, your first state you start from is all spins down, and then instead of the Cooper pairs, you have the magnons, so you start flipping the spins. And so in the first state, you just flip one spin in all different positions, and in the second state, you flip two spins until you flipped all the spins. And again, this is the operator that implements this. And one thing I also don't have in the slides, but wanted to tell you is that both families, they also, they are this maximum spin for the Zeta states or maximum pseudo spin multiplet in this Hilbert space, which you could probably recognize here. So you start from all spins down and you just flip one to the spin. So this is the spin n-half multiplet. Now this off-diagonal long range order, basically what it is, by definition, it says that you take this expectation value, so this expectation value for the Eta states, or this expectation value for the Zeta states, and you measure it in different places on your lattice. And so in lattice side I and J. And to be called long range order, you have this expectation value not to decay quickly with the I minus J, with the distance between the sides where you measure it. But actually, since these states, the invariant states, they have this huge UN invariance, they actually have also the permutation invariance. So for them, it actually, this correlator doesn't only not decay, it also doesn't depend on how you choose the points where you measure it. You can measure right next on 2 neighboring sites or on 2 most remote sites, and you will get the same value. That can also be calculated analytically, actually. And so you, you can also, with a little bit of algebra, see that this is a consequence of this ON or UN invariance of this state. All right, so as a next step, I wanted to show you just a simple Hamiltonian built according to our recipe and in this Hilbert space. So the Hamiltonian is shown here. So again, it's in the big picture, it's this H0 plus OT, where H0 is something simple and it's actually By field, which splits the Zeta states and gives them integer energies according to their index in the family. And then the T's, so the T is just the hopping as we agreed, and here it's the nearest neighbor hopping. And then as O, we choose this operator here, which is a sum of the magnetizations of the nearby sites, and we also put in some randomness inside. And why we do this, the idea is that we, to highlight the properties of scars, we usually want the bulk of the spectrum to be ergodic. And so we want to remove all the, symmetries that are there. And this, by putting this randomness inside, we can achieve this. So this is just to show that you can have pretty simple Hamiltonians that can already have the Zeta states and the Eta states as scars. I don't know, maybe there were some questions so far, or everything's fine. No? As a next step, I would like to go to the TGU model, and this was actually the subject of our second paper. And so what is TGU model? So the TGU model is where you have the hopping. So then you have the Heisenberg interaction, just spin-spin, and you have the Hilbert interaction on site, and you have chemical potential. And it turns out, it's not obvious, but it turns out that you can rewrite both the Heisenberg interaction and the Hilbert interaction in this H0 plus OT form for the states that I've just talked about, the Eta and Zeta states. And that actually means that also the TGU model and all the models that includes this Heisenberg or Hilbert interaction, any linear combinations of these interaction terms, they all support these families of states as scars. And here I have the slide where I actually show this decomposition, and maybe it's too much to digest in just 1 minute, but basically I wanted, as a big picture, what we do, we have the Zeta states with some symmetry. And with respect to that symmetry, we decompose the TGU model, the standard TGU model. We decompose as H0, which just includes some constants, basically, and OT term, which includes hopping, which we know is made of generators of the symmetry group, but also other generators. So this is really just OT term. And then independently from this, the Eta states, they have different symmetry. And with respect to this symmetry, we can again do the decomposition of the same TGU model, but in a different way. And it actually, H0 looks very much similar up to basically 1 term there, I think. And then OT again includes the hopping, which is the generator, and then some other terms which can be written down as generators with respect to the symmetry of the Eta states. Okay, now when we do numerics, so basically the takeaway message from this is that the TGU model actually does decompose as H0 plus OT, and so these states become scars immediately in this model. But for numerics, we will add 2 terms. The first term that we will add is, again, as in the simple example, it's just the magnetic field. And the magnetic field, we already saw in the simple example that it splits otherwise degenerate Zeta states into this Zeeman multiplet. And then we will include this more involved term of OT form to break the symmetries. So it's built again as something times hopping, where something is again something like the nearby magnetization sum with some randomness inside. And so the particular form of this term is not so important. Important is that we wanted it to be pretty chaotic so that we can have the bulk of the spectrum pretty chaotic, so that the scarce states in the numerics and all the plots that we have, they clearly stand out in the presentation. One other important point, we have a lot of control of these scars in our system, because we know exactly their energies. We know the H0 that acts on the zeta states, and we know H0 that acts on the eta states. So we can actually calculate exactly the energies of all these states. And once we know the energies, of course, we know the gaps between the invariant states. And once we know the gaps, we can calculate the lowest common divisor, the greatest common divisor, and that gives us the period of the revivals, which is pi over gamma, where gamma is the amplitude of this By field that we added. And then for the eta states, it's given by the Hilbert U and the chemical potential. Now, again, since we know this energies, and recalling the fact that each of the families makes a maximum spin or pseudo-spin multiplet in this Hilbert space, we can actually write down the conditions when a one representative of each family will become the ground state. In particular, the all down state will become a ground state in the big system where this is fulfilled, or the all fields eta state will become the ground state when this is filled. And to understand this, it's pretty simple. You have the maximum spin multiplet, and then you turn on the magnetic field. And so if your magnetic field is strong enough, then one of the states will, so you just spread this tower more and more and more, and then at some point, one of the states will grow over the bandwidths of the Hamiltonian and will become the ground state. So there is no really rocket science here. So one other thing I find really nice that we have, we can in principle arrange such that these invariant states, they really can completely fill the low energy subspace of the model. So the idea here is to take something positive definite of the form OT and add it to the Hamiltonian. And so what will happen, the green states, the singlet states, they will not fill this at all. But all other states, they will fill this positive definite addition. And so basically they will just go up in energy while the green states will stay. So, schematically, it will look like this. So no effect on scars, other states go up. So what is this positive definite thing that we could add? The first most obvious idea is the quadratic Casimir of the group, symmetry group of these states. The problem with this is this quadratic Casimir often happens to be non-local, not very practical. But then you can also just take the square of two generators. So instead of so you take OT of the form TT. And then interestingly, the Hilbert interaction, if you rewrite it as H0 plus OT, it rewrites as this constants plus exactly this. You have one generator times the other generator. So in principle, by taking huge U, you could already achieve something like this, except that this Ki doesn't annihilate only the green states, it also annihilates some of the blue states. So you will not have this picture, you will have also some of the blue states unmoved. But otherwise, I think that's a pretty interesting idea. Maybe one could modify this somehow to achieve this effect by simple means. So now, if we do numerics on this model, we can actually confirm scars. So first, we can look at the spectrum, and we can look at the gaps, and we can calculate this gap statistics, which I think you're familiar with. And then we do find the value which is very close to GUE, which is essentially like complex random matrices. Then you can also look at, you can make a histogram of all the gaps in your system. And then you see that for very small gaps, you almost have no appearances of those, and that means that you have the level repulsion as is expected in well, strongly interacting chaotic models. So this is also good. So that basically tells us that the bulk of the spectrum is ergodic. And then if we look at our invariant states and plot the entanglement entropy, then we also find that they are far away from all the generic states. They stay at their low entanglement entropy. What else?
Was the model exactly? This was the TJU, or?
Yeah. So this is this TJU. Let me go back. Yeah, so this is the TGU, where we also add something to break all the symmetries, and we add something to split the zeta states into equidistant tower. All right, so then the other thing we can do, we can also really take some observable and measure it in all the states and find that it does differ a lot in the scarce states than all other states. And we can also do the time evolution and find the revivals, and then find that the period of the revivals is given by the greatest common divisor as expected of all the gaps between the singlet states. And then there are some sub-revivals that are given by some subsets of the scarce having also the common divisors. So everything adds up together well, but I think
the revivals, these revivals are not perfect, right? Or
yeah, they're not perfect because I admixed 5% of generic states into the initial state to see what happens. So if I didn't do this, if I started from just scarce, they would come back to 1 forever. There would be no decay. Yes, and actually I haven't said anything about this plot. This plot is when you take the same combination of just generic states, and then you see that actually this fidelity, so the overlap of the initial state with the time evolved state, instead of coming back to itself repeatedly, just fades out and never comes back.
But why does it take it that long to decay?
Well, I think the system size contributes to this. So I think the biggest systems that you have, the
or some energy scales, I don't know. Do you have some small, big ratio of parameters or something?
No, I was thinking that this is basically just the finiteness of the Hilbert space. As long as you have small systems, this is how it manifests. I don't think, well, we haven't really studied this. We were somehow already happy with this plot, so then we didn't play with the parameters that much.
And how big is your system?
So the biggest we did was 9 sites, but this plot was actually made for a smaller one, maybe 8 or 7. Yeah, and I also didn't say that what we do with this, we do exact diagonalization, since we don't really know anything about it, since the states are pretty, chaotic, high entanglement. So we don't know if any approximations would work on them, and we also need the whole spectrum. So we just did the exact diagonalization on this.
I mean, I'm still surprised that it takes that long to decay, because otherwise the rest of your spectrum looks super close to ETH. I mean, the thermal states look quite, there's very little kind of spreading around.
But it looks long compared to this period. But if I took gamma different, then I could increase this period, and then this would look small. So these units are in a way arbitrary, right?
Yeah, but I would expect, that one should, for a generic state, should decay to 0 on something on the order of whatever energy scales you have in your Hamiltonian, right? So something order 1, not order 10.
Mm-hmm. Yeah, well, I have to say that we didn't really study that much, this behavior of, not scar situation when you start from something. So it's possible that we chose some very special parameters. but I don't have any better explanation right now. But what I wanted to say is that, again, to appeal to this sort of philosophy of looking at the Hilbert space more than particular Hamiltonians, because these three families of scars, they actually, they just live in this Hilbert space, and so they become scars in any model that is made as H0 plus OT with the terms, with the generators that we wrote down. So we actually wanted this second paper to be like this Lego box where everyone can come and take the pieces of Hamiltonian they like and build the Hamiltonians with scars and be guaranteed that the system has scars. And indeed, we actually demonstrated explicitly for all these models in this table that some of the three families of scars become scars bearing. Now you could ask the question, what if you add some perturbation to your system? So what if your Hamiltonian is not H0 plus OT, but you add some perturbations? And so I had the master student do some numerics on this, and the perturbations we considered were on-site random potential or on-site random field or nearest neighbor charge interaction. And then, first you already kind of in advance could say that some of them will actually do nothing to your states because of their symmetry properties. And this is already great in principle. So if you have Eta states, for instance, on-site field doesn't do anything to them. This is great to know. But then also some of the first order contributions of these perturbations also vanish on these states. So this is another result. And then which order contributes first actually determines the scaling of the quality factor with the perturbation strengths. And the quality factor we define since we have these oscillations, so then we can ask how many oscillations do I have until the amplitude goes down below some threshold, and call this integer number quality factor. And then you can actually argue that it should be going as lambda to the minus 2 when the second order is the first order contributing, or minus 1 when the first order contributes. So these are some preliminary results on that. So now other generalization comes about if you say, well, so far we wanted OT to be Hermitian. What if OT non-Hermitian? What would happen then? And in fact, since it's still OT, the singlet states will not even notice this. So for them, nothing will change. So they remain stable and they do the revivals, but the other states now leave with a non-Hermitian Hamiltonian, and non-Hermitian Hamiltonian basically does not conserve the total probability density. So that means that this probability density will be either flowing out of the other subspace or flowing into that other subspace, whereas the scars, they sit untouched and don't notice anything. So this is, I think, this is the plot illustrating just this. So we have a real part of the eigenvalues, imaginary part of the eigenvalues, and we see that all the eigenvalues in this non-Hermitian system now become actually complex, but the scars that are marked with the red symbols, they all stay at the real axis, and so they don't get disturbed at all by the non-Hermitianness of the OT. So basically here I would like to summarize what we've learned so far, and to generalize about our group invariant scars. So basically one thing we know, and I think that wasn't known about the Eta states, for instance, this ON invariance of the huge symmetry of the states wasn't really pointed out before. And this ON, this huge symmetry, also includes the permutation symmetry, so that you can reformulate as storing your information very delocalized over the full lattice. And well, it could potentially be, could influence how you treat, how you work with this in terms of quantum information processing. So what other properties we have for our scars? We have exact wave functions for them, and we have exact revivals if we want. So that's another property. Now we can, since we know their energies, we know their wave functions, we can actually manipulate them pretty confidently. So we can move them around the spectrum. We can make some of the scars ground states. And another property is this long-range order, which is again a property of just these states being maximally spread over the lattice. And now other property of our construction is that these states, they are scars in any model of the formational plus OT in this Hilbert space. And so there is a huge freedom, there is a huge family of Hamiltonians that have these states of scars. So this is all I wanted to say about the spin 1/2 case on the lattice. So maybe that could be a place to, if there are any questions. And then I would switch to the multi-band case, our latest work right here. So basically here we ask the question, what if we have lattice again, and we put on each side Majorana fermions, and we have M flavors of this Majorana fermions? What will happen then? So otherwise, the construction is more or less similar to what we just talked about. So again, we will think about Hawking to be the generators and the corresponding symmetry groups. But now we have multibands, and now we have Majorana fermions. So one consequence is that the green subspace of invariant states, it will now be much larger. So before we had 2n+2 invariant states, where n is the number of lattice sites. Now it goes as n to the m squared roughly. So this hopefully gives us the possibility to arrange something like this, where you have a densely populated low energy subspace of your system. And then also what we notice is that we had before eta states and zeta states. Now they become this generalized eta and zeta states. So I will not show you the exact expressions, and they become more and more complicated with increasing m. But in principle, they are sort of descendants of this simple eta and zeta states we just had before. So now, again, the Hamiltonian that we will consider, the multi-band Hamiltonian, in the big picture, what you want to remember is that it stays H0 plus OT. And well, maybe you don't want to really stare too much at the particular form of the Hamiltonian, but I can tell you that how you arrive at this. You take the Hilbert model written in terms of complex fermions, then you rewrite it in terms of Majorana fermions, and then you ask yourself, what if you have now more flavors of the Majorana fermions? So then you arrive at something like this. So this is actually just the chemical potential from the regular Hilbert model. This is the generalized Hilbert interaction when you have more flavors, not just up and down spin. This is the kinetic energy you already had in the Hilbert model. And then this is the OT term that we add by hand to break the symmetries. Okay. And now we again do the numerics on just 4 sides, and m equals 8 is the number of Majorana flavors. And we get, again, the plot that suggests that we have many body scars, except that there are some features that I will expand a little bit more as we go. But one first feature is that we have now these 2 generalized eta and generalized zeta families that separately appear as scars simultaneously in this system. So here they are shown separately. So then we can again look at the spectrum, again see that there are no 0 gaps which suggest level repulsion and chaotic bulk spectrum. We can look at the average level statistics, see that it's more or less random metrics. So again, the bulk spectrum is chaotic, we conclude from this. And then some of the features. So I think this is probably correct me please if this is not true, but it seems like this is the first example of the system where scars are not equally spaced, except if you do Shimori and you can put them any way you want. But here, well, besides from that, this is the first example of not equally spaced scars. Although we know exactly, for small m especially, we know exactly the spectrum of the invariant states. And so we know these conditions on the chemical potentials in U that would make the gaps between them have the common divisor, and then we have the revivals if we wanted to. So this is one first interesting thing. The other interesting thing is that, well, we conjecture, we haven't proven it rigorously yet, but we are pretty sure this is the case. There are degeneracies within this singlet subspace, within the scar subspace, that cannot be lifted by local interactions. And this is, again, could be a resource possibly for quantum computation. In principle, you have these topological subspaces in which you do the topological quantum computation. So possibly these degenerate subspaces could also be something like that, could have more protection, maybe, hopefully. But I think this is also a new feature that we at least haven't seen before. And then the other feature is that we have quite some number, 2 to the power m½ of the product scar states. So those scar states, they have 0 entanglement entropy, and they are product states. So if anyone ever wanted to do an experiment on this, probably they would think of these states as easiest to initialize the system to. And those product states, they're actually pretty simple. So you have many flavors of Majorana fermions, and then you just fully fill these flavors independently. And then there are 2 to the m½ possibilities of do this for different flavors. But in principle, those are simple, like all filled or all empty for particular flavor states. And well, if some experiment wants to do this, then maybe this could be useful. So we are coming to the end, more or less. So what I think would be interesting to do regarding the spin 1/2 case. So remember, we have this all different generators that we wrote down. Some of them look like this. They look like spin orbit coupling. Some of them look like this. And our hope is that just maybe it would be possible to build some interesting models that have some properties following from this spin orbit coupling, let's say, plus they are guaranteed to have the scars. So maybe the interplay of those two things could be interesting to study. So that's one interesting thing. So then it would be interesting to think more in detail how you actually use those things, those states for quantum information processing. Another direction is open systems. So we see that in non-Hermitian systems, many body scars are stable. But what does it mean for real open systems? Because real open systems, usually you have it and then you make some approximations and only then you get the non-Hermitian Hamiltonian. So can we go back from our non-Hermitian Hamiltonian and end up with some real open system and see that the scars are stable there? That would be very interesting to study, I think. And multi-band models. So I've shown you one example, but there is more to do, and there are more open questions there. So with that, I come to the acknowledgements. Again, the team that people have been involved, the different agencies that helped us, and the archive postings where you can find more details. So thank you so much.
Great, thanks a lot. Any questions for Kiryl?
Yeah, I have a question.
Yeah.
Could you comment on the relation between your construction and what is addressed in this commutant algebra framework? I don't know if you're familiar with it.
Oh, yeah, absolutely. So, well, I haven't fully digested it, I would have to say, but the way I see it, their construction is very similar, except that we have the algebras that are Lie algebras of some groups. For instance, UN. And this fact that we not only have the algebra, but we also have the group, gives us the possibility to actually construct the invariant states, because the representation theory is known for the groups well. And what they do, I think, is they abandon this requirement that there is any group associated to the algebra. They just consider algebras. So they have one algebra of Hamiltonian terms and the other algebra of sort of conservation quantities. And from that, you get a very equivalent, very similar formulation to ours. But the main difference is that you don't refer to groups anywhere. And that means you can cover probably more systems. You cover the systems where there is no group associated to the algebra, but you can still have the scars, but you don't have the representation theory of for groups to help you build the actual scars. So I think this is the trade-off. You have more generality covering different systems, but you have harder time actually writing down the wave functions for them.
Okay, yeah, that makes sense. Thank you.
Any other questions? I wanted to ask about this last results where you have the red and blue states. So the spectrum of that red and blue thing is completely solvable. You know exactly what it is?
It's solvable with the help of Mathematica. So some expansions you need to do with Mathematica, and it becomes harder and harder as you increase the number of flavors. But in principle, for the ones that we could possibly do numerically, we know the full spectrum.
So it's always integrable. I mean, there's no way to make that non-integrable in itself, right?
Well, it's integrable in the sense that we can solve it. We haven't done any statistics on this to see.
Yeah, but probably it would be like Poisson, right?
Yeah, most likely, yes. So you would like to have it non-integrable so that we don't know the spectrum. No, I think that should be possible. Just you need somehow uglier looking H0. We started with the H0 that was just generalization of the chemical potential of the Hilbert model. But if we add there something that still satisfies the general H0 conditions, but makes it harder to solve, then I don't see a fundamental abstraction for that. I think, yeah, so I don't think it needs to be integrable. I think it will decouple, but it may not be really solvable.
Do we have any other questions? Looks like not, so let me stop the recording.